I suspect what's really changed is that the efficacy of the phytases has improved. Their ability to release phosphorus and calcium has improved, and so we're seeing better release of these nutrients from phytic acid. And people are now tending to use a little bit more phytase in the diet than they were right at the very beginning.
Hello and welcome to the Poultry podcast show. Today I am here with Dr. Mike Bedford. He's going to talk to us about some of his expertise areas, which are in enzymes and some different nutrition components such as calcium and phosphorus in poultry diets. But first, I'd like to take a minute to welcome you to the show. Welcome.
Thank you very much. Thank you. It's great to be here. And actually, I'm really quite excited to be on this podcast. I was just looking at Sunny Knowles and thinking what a cool life she's had, and thinking I can't think that mine's going to be anywhere near as interesting. But it's a great venue and it's a great medium to actually get to know people.
Yeah. I really love talking to people and hearing about what they do. Everybody has some really interesting experiences.
Yeah.
So how did you get into chickens, to the poultry industry?
Well, it's funny, actually. I was on holiday when I was a teenager, and we happened to be fishing, and a farmer came up and said to me, he said, "Are you guys looking for a job?" Literally said that to me. And of course we were, at the time, we were looking for a summer job, and he gave us a summer job on a farm, which is a mixed farm, included pigs. And I enjoyed it so much, he suggested that I went and did an animal science degree, because at the time I was thinking of doing something more veterinary or medical related. And so I chose animal science and got into animal nutrition at university. And then the reason why I went to chickens was actually quite funny as well, because in the final year of an undergraduate degree at the University of Nottingham, which was where I went, I was given a choice of 3 different topics, and it was either a ruminant study or a pig study or a chicken study, and everybody wanted ruminant. And what you had to do was get back to the university early in the year to select the project you wanted. And I missed the date by 2 days, and all that was left were chicken projects, and I was absolutely gutted. It wasn't what I wanted at all. I wanted ruminant. I ended up with chicken project, and I actually realized, this is fantastic. It works. I love it. They're great animals to work with. They're intriguing. And that's what started me on my life with chickens. So it was real serendipity. It was not by design or by anything to do with my background. Because my dad was a head teacher and my mum was a sales manager. So yeah, nothing in the family put me into that. So I bet you never had a start like that.
No, just having a nice stroll along the road, and hey, you want a job? Yes, I do.
Exactly. Yeah, exactly how it turned out.
Oh gosh, that is awesome. So can you tell us a little bit about what you're doing your role currently?
Yeah, so at the moment I'm the research director at AB Vista, and we supply enzymes, so phytases and xylanases and other enzyme products into the feed market. And my role is really to have a look at trying to understand better how they work, what makes them fail when they fail, and they do fail. They don't work all the time. Sometimes, they don't deliver what you're hoping they're going to deliver. Understand what those things are that can make it fail, and also understand how to use them better and get the optimum results out of the product. And in doing that, you understand more about the mechanism of how the enzymes are working in the animal. And by understanding the mechanism, it gives you some pointers as to, well, how do we improve on the current products we've got, for example.
Yeah. So from my understanding of phytases, it's one of the most common enzymes added to poultry diets, but also one of the oldest, correct? I mean, they've been around for a long time.
They have. They actually are predated by xylanases. I mean, if I go back to where did I start? I did a series of degrees in Canada, and then finished up doing a postdoc in Canada on the use of xylanases in rye-based diets. And rye is a particularly sticky grain, and it was something that was grown in Canada, and xylanases broke down the sticky or viscous material in rye. And as a result, birds could digest that material much more effectively and grew more quickly and more efficiently. And at the same time, the enzymes were being developed for barley, beta-glucanases, and that goes back even to 1962, where people had identified what the problem was with barley. But commercially, they didn't really take off until a company in Finland was able to produce large enough quantities of beta-glucanases, which were targeted in barley, and they had close ties to the feed industry in Finland, and it enabled them to really upgrade the use of barley in chicken rations in particular. And that was the beginnings of the whole feed enzyme industry. So about 1984, 85 is the first time that they were ever used, not in large quantities. And it took maybe 5 or 6 years for that to catch on. I was doing my postdoc in Canada in 89, and I moved to the UK in 91. And really was on the crest of the wave that just started pushing beta-glucanases into barley rations and then xylanases into wheat rations. And it was NSPases, or fiber-degrading enzymes, which took off first. Phytases were fairly close behind, but they never had the market share, really, until the price of the phytases dropped to become economically attractive to pull into the diets. But now you're right, phytases and NSPases are, it's probably 50-50 in the marketplace in terms of volume, so or value that's being sold. Yeah.
So I feel like you've seen years and years of use and change of these enzymes, and even in what we're using for feedstuffs for the diet, just as times change and we go through different byproducts or different grains, especially based in the world. So can you tell us a little bit about maybe historically how they've been used and trends that you've noticed, or basically how have we made these enzymes better?
Yeah, it's really it is an interesting evolution. Well, it might be interesting. It depends on whether you're interested in it or not. But when we started in the 90s selling enzymes into the commercial world, we were lucky in some respects in that the varieties of barley and wheat, because let's face it, back in that early 1990s, we were not selling enzymes into corn or maize-based diets. And the reason why they were selling so well into barley and to wheat-based diets was because the varieties that were available were really quite sticky. So when birds ate them, the cell wall material dissolved. It was viscous material and it would slow down digestion. But the most notable thing was they had very sticky, wet droppings. And so when you put these enzymes into the diets, you could see straight away you were having an effect. So it was really easy to sell those enzymes at that point in time, not only because the performance was much better, but also because you noticed an immediate improvement in litter conditions. And as a result, things like hock burns and foot pad dermatitis were almost eliminated. So that was very lucky and very easy. And the interesting thing is, if we look at the varieties of barley and wheat that are available today, they're nowhere near as sticky or as viscous. Just breeding has taken those characteristics, not completely out of those grains, but largely out of those grains. And so if we were trying to start this industry up again today, it would be much more difficult in barley and wheat, for sure. And then, as time went on, we realized that even though maize wasn't viscous, it did respond to xylanases, and we started to realize that we could, with prices of enzymes dropping, you could actually get cost-effective responses even in maize-based diets. And that started our search for, well, how are these working? Because if maize isn't viscous, why would a xylanase, which reduces viscosity in a wheat-based diet, why would it give you a response in maize? And we're still trying to pull that apart today, although we've got a much better idea, obviously. But yeah, so we were lucky when we started, I guess.
So have you seen that the cost of the phytases is going down because the efficacy is so much better, or the production is also becoming more efficient?
I think it's a combination of many things. The phytase market would never have taken off if phytases remained at the prices that they were at when they first came in. When they first came in, they were being used to enable animal production in areas where phosphorus pollution was such that farmers were told if you did not reduce the phosphorus that you were putting on your land, you had to. So the only way they could do that was by reducing animal numbers, and dramatically, which would have been catastrophic for the Dutch and Northern German industries. And even though phytases are expensive, it is actually very cost effective to use these products and enable greater numbers of animals to be concentrated in the same area and still stay below the phosphorus deposition on the land limits. And it facilitated basically a very successful animal industry. But the price of the phytase was such that at that time that it wasn't really competing out the alternate phosphate sources in the diet. It's like monocal, dical, D4. But yeah, with competition and with the development of better strains and better enzymes, you're right. What happened was for $1, you were getting far more phosphorus release, which becomes cost competitive. And then we start to see phytases being used worldwide.
What do you think the interaction with how the genetics have changed as well in the birds? Do you think the birds themselves are getting better at using, non-phytate phosphorus, or is it really driven by the enzyme use?
That's a good question. My honest answer is I can't remember if I've seen any data on old strain birds versus your random bred strains versus modern strains. I'm not sure that the bird's gone any better at using phytate phosphorus, but the bird's requirement for phosphorus and calcium on a daily basis has gone up because they're growing quicker and they're putting bones down quicker. So, you've got to deliver the nutrients quickly enough to enable proper bone growth. I suspect what's really changed is that the efficacy of the phytases has improved. Their ability to release phosphorus and calcium is improved, and so we're seeing better release of these nutrients from phytic acid. And people are now tending to use a little bit more phytase in the diet than they were right at the very beginning, when you don't muck around with phosphorus. If you go deficient in phosphorus, you have it. That's right. So at the very beginning, people were very cautious, and they would only be taking out 0.05, 0.08, or 0.1% available phosphorus. And now people are realizing, well, this stuff works. We can go higher and higher and save an awful lot of money. So I think, the efficacy of the phytases has changed. I think what else has changed as well is, if you look at a typical diet about 15, 20 years ago, there's some really good reviews which were looking at what are the calcium and the phosphorus levels in those diets. Phosphorus is expensive, so people tend to be quite good at making sure that measured phosphorus level is what you're targeting. Calcium's pretty cheap, limestone, very cheap. And if you looked at what you'd actually find in the diet for calcium versus what was actually targeted, there's usually quite a bit more. And that makes things more difficult for phytase to work effectively. So people were rightfully cautious in what they were giving phytase. Nowadays, people are beginning to realize that high levels of calcium in the diet are actually detrimental, not just to phosphorus digestibility and phytase effects and performance, but also to performance as well. So there is quite a significant move to remove that calcium excess that's present in a lot of broiler diets. And it's quite interesting. I was just in Bangkok 2 weeks ago and was talking to some companies, and they are really low in their calciums now in their starter diets, probably 0.2 or 0.3 lower than they were back in the 90s. Really interesting reductions in calcium levels. Yeah, I think because they were oversupplying in the beginning, and they're beginning to realize that actually, if you're feeding for optimum gain, it doesn't necessarily mean optimum tibia ash. Tibia ash is not necessarily tibia function. And, is that bone good enough for the bird? Is the bird in a good welfare status? Is it healthy? Is it not got any problems? That's fine. You've got a level at which you can deliver that kind of a tibia ash, which is a target of calcium and phosphorus requirement. But if you overfeed calcium and phosphorus, what will happen is they'll just keep on depositing calcium and phosphorus in the bones. So if you want to maximize tibia ash, you actually feed enough calcium that it depresses growth performance. It's in excess of performance. Think of it a little bit like fat. If you overfed a broiler back in the 90s, early 80s, they would just put on more fat pad. So right. If you think about the fat, it's the tibia is the bone is a store of calcium and phosphorus, and if you're in excess, you may well put a lot more down just to have some for a rainy day, and that doesn't necessarily mean it's what you need.
Right.
because you don't need a big fat pad, but
Yeah.
maybe you don't need that much calcium and phosphorus in the bones as long as you're supplying calcium and phosphorus every day in the diet. Yeah.
Yeah. So what do you think about optimizing those three? Like what are your best practices involving those nutrients?
Yeah, you're absolutely right. I mean, you have to use phytases with a proper and careful assessment of what your calcium and phosphorus levels are in the diet, what matrix you're going to apply. And I don't think there's many people who do not apply a calcium matrix when you use an enzyme. In other words, you're reducing both calcium and phosphorus levels when you're using phytase, because phytases will release both nutrients. And to some extent, sodium. Sodium is something you got to keep an eye on as well, because there's a sparing effect on sodium, which can have an influence on wet litter.
So among all of the phytases that are in existence, they're all generally working on the same mechanistic pathway, like liberation of the non-phytate phosphorus, and then iron and phosphorus and different chelated micronutrients are coming off. So are there any things that have changed about the enzymes over time that have made them more efficient, just based on like the chemistry?
Yeah, I mean, we've evolved phytases to be more effective in working in the functional environment of the proventriculus gizzard of the bird and the crop. There's a little bit of phytase activity in the crop, but the majority of it is in the proventriculus gizzard, and that provides significant problems. Well, actually, let's start with the diet. The phytases, first off, got to get through the pelleting process. So,
yes.
Yeah, so you've either got to be thermostable, or you've got to have some coating effect around yourself to protect it, or you can spray on post-pellet. So they're the ways around it. Now, if you've coated your phytase, you really need that thing to release quickly, and if it's going to function in the proventriculus gizzard. So that's the first problem you've got to get around. The second problem is, once you're in the proventriculus gizzard, you have an interesting environment, which is low pH and cyclone pH as well. It's not constant. It can go below 1 and it can go above 4. And the phytase has got to work in all of those situations. And there's pepsin there, which is a protease, which can break down a lot of proteins. And some of the early phytases, in fact, a lot of them, were quite susceptible to pepsin attack. So some of the things that we've evolved and improved on is thermostability, but also pepsin resistance, so that the enzyme can stay around longer and do more damage to the phytic acid. And then I suppose the next component of what makes a better phytase is how well it attacks the phytate molecule, because phytic acid is inositol hexaphosphate, and in order to get all the phosphates off, you've got 6 phosphates on there. You've got to take all 6 off if you're going to get all the value out of that diet. And phytases will take the first 5 off and leave the last one. The last one is taken off by phosphatases in the small intestine. But phytases will take the first 5 off, and they vary. These phytases that were in the market and still are in the market will vary quite significantly, not necessarily on how quick they are going from IP6 and take the first phosphate off to IP5, but they vary in speed of how quickly they'll take IP5 to IP4 and 4 to 3.
Oh, interesting.
2 to 1. So I always like to say that taking phytic acid down to inositol and 6 phosphates is like a marathon. And what we tend to measure when we look at assays in the lab is the first phosphate coming off. So you've looked at a marathon, but you've only viewed the first mile. You haven't looked at what's happened for the rest of the race. And so some phytases might be very, very quick in the first or second phosphorus coming off, but really slow down later on. And that's something we're working on and trying to improve in the next generation of phytases after this one.
So something that I've always wondered, just because of how much is going on as the bird is digesting, can something that has been unchelated at the beginning of the gut, so let's say they got phosphate 6 and 5 off, can it rechelate by the time it gets to the end? So is there a way that phytases also prohibit that from happening?
That's a really good question as well. I mean, it depends. So the interesting thing is phytic acid IP6 is an incredibly strong chelator for an awful lot of minerals, and it's very strong for things like zinc and iron. It's less powerful for calcium, but because there's so much calcium in the diet, it just by mass average is going to be hitting calciums and binding calcium. So we put a calcium matrix on because we know that the phytic acid will bind it. Now, if you take one of those phosphates off and you make IP5, you quite significantly reduce the binding capacity for calcium. And if you take off another one or another two, it pretty much won't bind any calcium. So once you get down to IP3, it's not an issue for calcium. And that doesn't matter what pH you're at, because there's another thing that comes into play here. If you're at low pH, then the ability of phytic acid to bind any mineral is less than if you're at a higher pH. And the reason is because phytic acid becomes even more negatively charged as the pH goes up. It starts releasing hydrogen ions and more of its phosphate groups become negatively charged. So imagine it's a magnet that's just getting stronger and stronger. And as you take off the phosphate, making IP6 to IP5 to IP4, it doesn't change the fact that when the pH goes up, that IP4 becomes more of a magnet for whatever's available. Now, at very high pHs, very high, as you move into the small intestine from the gizzard, the IP3 and IP4, which is quite soluble, and it's not coordinating anything because you've taken off enough phosphates that at the low pH in the gizzard, it's not really coordinating anything. It's highly soluble. Most of it is in solution. It will move into the small intestine, and all of a sudden the pH goes up, and it becomes a bit of a magnet for things like zinc and iron. And when we use very small light amounts of phytase, or use amounts like 500 FTUs, which is a common dosage use, what you'll see is you'll reduce the IP6 levels considerably, but you will actually increase IP4 and 3. You've pushed that IP6 down to IP4 and 3. So you're removing the problem from the calcium's viewpoint, but you haven't removed the problem from zinc or iron's viewpoint. In fact, you might have created a little bit more. So yeah, it's really interesting. And that's where some of the benefits of superdosing are coming from, is if you think of the lower esters, the IP4 and 3 and 2, as still being potentially problematic, then you need to feed enough phytase to get rid of all of that. And in typical corn soy diet, that's a lot more phytase than we use today, a lot more.
That's really, really interesting. So there seems to kind of be a cliff, if you will. If you can at least get the first two phosphoruses removed, then you're in better shape.
You're in better shape, but you're not perfect. Yeah, exactly. It's a threshold. It's a threshold for the first problem. And then you've got a second problem, which is what are you going to do about the binding capacity for the lower esters for the other minerals. And then you've got another problem, is that if you want to create inositol, and we haven't talked about that yet, if you want to create inositol, you've got to present the small intestine with IP1, because IP1 is broken down only really by duodenal and jejunal alkaline phosphatases and some acid phosphatases from the bacteria in the gut. And the gut phosphatases are not particularly good at breaking down IP2. In fact, they don't touch them. There is a gut phytase, but that's not particularly good at working under the conditions that we feed the animal, high levels of calcium. So really and truthfully, if we want to see a lot of inositol being released, we have to put a lot of phytase in to make sure most of the IP6 has got all the way down to IP1 before it comes out of the gizzard. And in a recent paper by Ruben Crisaldi has shown that you're still getting responses in inositol levels going up by going to 40,000 units of phytase. And remember, currently we're only at 500. So I'm not saying that's economically viable, but who knows? As you get to better and better phytases and we're producing them more effectively, we might see ourselves in 10 years' time at 5,000, 10,000. Certainly, Ruben's work, he did show performance benefits going to 13,000 units of phytase. So, yeah.
That's really cool that they're continuing to do some of that work to understand the upper bounds and some of the other limits, or understand how the enzyme completely works. And it's been around for a while, so heck, keep going.
That's a really good point. So you would have thought that you'd know everything about the stuff by now, but actually we're only beginning to. I mean, one of the coolest pieces of work that's being done at Arkansas by Sami Dridi's lab and Alison Truitt-Ramsey is looking at what happens with the inositol as it's released and getting rid of all the phosphorus off the phytase. If you feed super high levels of phytase, you change the way the blood can carry oxygen. and it looks like, and so in syndromes like woody breast, which is partly down to poor oxygenation of the breast tissues, by feeding super high levels of phytase, we change the ability of hemoglobin in blood to release oxygen in deeply oxygenated tissues. And that's because in the chicken, the chemical which enables this release of oxygen from hemoglobin is inositol pentaphosphate. So it's IP5. So here's the irony. In the gut, you don't want to have IP6, 5, 4, 3, 2, or 1. You want to get it down to inositol. Once inositol is created, it can be absorbed. And once it's in the blood and it gets into the red blood cells, it's rebuilt back up to IP5, where it binds to hemoglobin, and then it pushes oxygen off hemoglobin in deeply anoxic tissues and enables them to survive. So we see reductions in woody breast. And the latest work Alison Ramsey's been working on is femoral head necrosis, and it looks really cool for that. It's reducing the problems from that particular issue, which again has an oxygenation issue in terms of the growth issues of the bone.
Gosh, that is so interesting. Well, it's always surprising, with the metabolic processes to break things down small enough so they can be actively or passively or, however absorbed, repackaged to go back to make the thing that they were before.
Yeah, it does seem bizarre, doesn't it? There's a lot of work to get it down to its initial, exactly to its constituent parts, and then you go and rebuild it all back up again. But it's a different restructuring. It's quite interesting because the IP5 is a different isomer in the blood compared to the IP5 that you'll find in the gut. Yeah. So I don't want to bore you with the chemistry, but basically the phytases will not take off the phosphate in the 2 position, which is quite useful because the phosphate in the 2 position is quite critical for biological functionality in animals. So we build them up. When we say IP5, it's not the same one that you'd find in the gut as a result of phytase activity.
Gosh, well, that's good because then it could technically be a signaling molecule, right, in the gut with things going on. So maybe
we don't want to be doing that in the gut, which is good.
No.
Yeah.
So when we talk about the complexity of digestion and absorption, even within the context of the phytase, what do you think is going on alongside the phytase when we say that there's more minerals that are or are not chelated or released with the microbiota? I mean, there's got to be changes, right, with the way we're feeding diets and then the way the microbiota respond, right?
Yeah. It's really complicated. You're right, absolutely right. I mean, I think it's the mineral released from the phytate means that they can be absorbed. If you're feeding a high enough level and you're releasing the zinc and you're releasing all the other bits, particularly iron, and it's being absorbed high up in the gut, then it's not available for bacteria down in the back end of the gut. The other thing is if you're breaking the phytic acid down and you're breaking it down to the point that there's very little phytate phosphorus left, then you have an interesting issue for the microbes in the back end of the gut who are relying on phytic acid as their phosphorus source because they do produce phytase. Pigs in particular are very good at producing phytases in the hindgut. And, in pigs, you might see virtually no phytic acid being digested by the terminal ileum, but it's all gone by the time you get to the feces. And it's a phosphorus source for bugs. So you're right. If you've used a phytase, you're changing the dynamics of what's available for which sections of the gut. And the other elements which are interesting for phytase is the inositol effect. Some of the inositol is made available. Is that being used by bacteria? We don't really, we know, I suppose it's a truthful answer at the moment. But phytases at very high levels are also improving protein digestion, which is removing amino acids or protein from potential fermentation in the ceca. So yeah, you're absolutely right. Phytase is having a significant effect on nutrient supply to the distal bacteria for sure.
So what do you think about the combination of different xylanases, the beta-glucanases, and phytase? So are we inadvertently altering the microbiome because of what we can offer it for food?
Yeah. I mean, goodness, how you get into complexities that I don't think anybody really understands. Yeah. I think I've been trying to simplify what the heck are NSPAs is doing, which are of value to the microbiota, because that's really what the question is. And really what they're doing is they're taking large insoluble and large soluble fiber fragments, breaking them down and making them into smaller fragments, which are much more fermentable. So it's effectively what fiber degrading enzymes are doing is enabling better fiber digestion. Now, digestion is the wrong word because it's being fermented, right? But if they're working well, they are taking insoluble fiber, making it soluble, and they're taking soluble fiber and chopping it up so it's more edible by bacteria. And by making it smaller, it's more likely to get into the seeker in the first place, because the seeker is a really good sieve and it won't let large particulates and it won't even let some viscous sticky molecules go in. So you have to be small, and it has to be soluble mostly to get into the seeker. So enzymes are fairly good in chickens in that regard. They'll chop it up and put it into the seeker. How they interact with phytases, phytases are working in a completely different plane, but they're changing as I said, the plane of nutrition will go into the seeker as well. So the combination of the two seems to be quite effective. In fact, in Alison Rams's work, we were looking at, so this is the one with BCO, there was quite a significant reduction in BCO problems as a result of the combination of effectively a xylanase and a phytase. And it seems like the theory is that the xylanase is improving gut integrity by feeding the bacteria and enabling them to produce the volatile fatty acids, particularly butyrate, which keeps the gut in good condition. So there's less likelihood of translocation of pathogenic bacteria into the bloodstream and onto the bone. And the phytase was, as I said, was providing the inositol to maintain oxygenation of the bone structures, so they didn't get the problem in the first place, or didn't get the injury site in the first place. So yeah, there's quite a bit of interaction between the two. And then some people, and I'm not sure I believe it, but I think it may well be the case that phytic acid in cereals is enveloped in cell walls, which are made of fiber. If you break fiber down, you expose more phytic acid to attack by the phytases. So that's definitely a possibility as well.
Yeah. So, traditionally or typically the value of fiber is low in poultry diet, especially without some of these enzymes that can help the bird use and the microbiota use and change the architecture of the gut. So what do you think about the future or the current potential value of fiber? Like, should we look at fiber differently?
Yeah, I absolutely. I mean, you guys in the US are probably, we always like to say in Europe, well, we banned antibiotics back in 2006, but you've gone even further with no antibiotics ever. And, you are actually in a more stringent situation than we are even. And when you take that constraint on pathogenic bacterial growth out, then you have to really balance the microbiota so that you've got a balanced microbiota that can keep the pathogens at bay by natural means. And the natural means here means providing the bacteria with a substrate which is carbohydrate in nature rather than protein in nature. And you can reduce the amount of protein going into the seeker by feeding phytases, maybe proteases, and even xylanases will improve protein digestion. So that will reduce the supply of the bad stuff. But then how do we increase the supply of the good stuff, which is the fiber? Well, fiber degrading enzymes, as I said, will break up the insoluble fiber, which ordinarily would have gone straight out and gone into the feces, break it up and make it soluble, some of it, not all of it, and chop it up so it's smaller, so it's more digestible, and it's more rapidly fermented by bacteria. And that keeps the balance of fermentation firmly on the right-hand side, where you're looking at volatile fatty acids being produced rather than branched chain fatty acids, which are indicators of amines and polyamines and phenols and what have you, which are all the nasty protein fermentation products. So yeah, fiber is definitely something we've got to look at as being our friend now rather than our foe. But it is interesting to me. Fiber is such a bad word because it makes it sound like it's one thing, right? And it's so complex, and some fiber is inert, doesn't do anything. Some fiber is definitely an anti-nutrient, particularly viscous fibers. And some fiber is your friend, which is the fermentable fiber. So you've got one name for a complete smorgasbord of effects. Yeah.
So we can use or we have used fiber for different types of diet, sometimes as, a filler, if you will, or increase fiber to have an effect on the bird, such as, get them to go into a molt or something like that. So what do you think? What do you think about increasing fiber just in any of the production diets versus a breeder sort of diet? Like, what are the different things to think about?
Yeah, I mean, you're in an interesting situation with that. So I was saying there's an optimal balance between fiber fermentation and protein fermentation. The interesting thing is that if we look at our diets here in Europe, which in the UK are wheat-based, there's lots of fiber that we can break up and loads of soluble fiber produced by xylanases, and there's, we don't run out. Corn soy is completely different kettle of fish, because when you look at the soluble fiber in corn, there's very little. And when you look at the effect of xylanases or even, complex fiber degrading enzymes on corn, we tend to release a lot less soluble and therefore fermentable fiber from corn than you ever would from wheat. So there is an interesting issue here with what you made a really good point. You put in a lot of fiber for breeders, but that's for a totally different functional effect. It's really gut fill and making them, not trying to get rid of hunger pangs. What we're trying to do now is add fiber to broader diets, but really to present them with a fiber that can be broken down and can be digested probably better than you would with just the fiber in corn. Now, it's not to say that there isn't fiber in corn. It's just that it's not particularly susceptible to breakdown by the enzymes we've got today. And in fact, that's one part of a big research program we've got going at the moment is, well, can we do something about that? Can we actually find enzymes which are much more effective at targeting corn specifically? Because corn is really interesting. The fiber is not the same as in wheat or barley or any of the other grains. Sorghum's quite similar to corn. It's really complicated. And because it's complicated, enzymes are simple. They don't like complicated backbones. And unfortunately, corn, which is your favorite cereal, is very complicated and much more difficult to break up. So yeah, it's something for the research.
This past weekend there was a beef cattle show in Ames, and my husband and I went because my friends were there with their kids showing it. And no matter what species you look at that's been fed corn, there are always remnants in their feces. So corn just seems to be one of those incredibly indestructible fiber types. Like, if it can get through a rumen.
Yeah, that's right. There's always a bit that gets through, isn't there? It's just incredible. Yeah. And the remarkable thing is it's dependent upon the corn itself, obviously, but individual animals, individual birds differ massively as well. So, we can see the same in the feces of broilers. Sometimes you take them, you look under a microscope, and some birds there's completely undigested cells in there. How did that get through? That's incredible.
Oh no, corn has always intrigued me that way, because it doesn't matter what the digestive setup is, it somehow finds a way to survive.
Yes. Yes.
So in your role at looking at different enzymes and efficacy, what are some of the challenges you face with getting people to use the enzyme correctly? Like, what would you like a nutritionist to know to get a better benefit from using any of these enzymes?
It's really difficult to. I would hate to be on the other side of the table. Let me put it that way, because first off, do you believe this guy? That's the first thing that you're thinking, and the second thing is he's telling me to do something which, if his product doesn't work, I'm going to have some major problems here, because you can take a little bit of energy out of your diet, and what'll happen? Maybe your FCR will drop out a bit, but you're not going to have leg problems and broken heels or whatever, which is what's going to happen if you make a mistake on your phosphorus and calcium levels. So what do we try to do? We try to show them the data that we have, the scale of the amount of data that's out there. Also, here's an interesting issue as well. When people go to higher levels of phytase and you're trying to convince them to save even more money by taking more phosphorus and more calcium out, there is a concern that if you are using a phytase and you're trying to get, let's say, 0.2% available phosphorus from your phytase, you've got to be very careful that you've done an analysis of their diets and made sure that there's always plenty of phytate phosphorus there to provide that 0.2 when you put your phytase on it. And I never like to see somebody going for 90% phosphorus conversion. So a typical corn soy diet might have 0.24% available phytate phosphorus in it. So if the phytase worked and got 100% of that phosphorus off, you would get 0.24 available phosphorus from it. I don't like the idea of somebody coming in and using on that diet a phytase and expecting to get 0.225 or 0.23. It's just too dangerous because nothing is that efficient, and there's always going to be some dropouts. It might be that for whatever reason, the batch of soy you pulled in for that particular diet had a little bit less phytate phosphorus than you expected, and then all of a sudden expecting the enzyme to deliver more phosphorus than there is phytate phosphorus in the diet. So the first thing is to really give them the tools and the information they need to understand where the limits should be. And then the second thing is to go through how to make the phytase work effectively. So it's what we've just talked about earlier. It's you don't just take a phosphorus matrix, you've got to take the calcium matrix with it, because if you don't, a high calcium diet really degrades the ability of the phytase to work. So you might think you're protecting yourself, but you're not. You're actually making things worse. So measurement of what you've got in your diet, and really just looking at the data and listening to the individual who's trying to sell you the phytase, what their arguments are. And then as everybody does, take a safety margin out. 90% of people do. And to be honest, if I was on the other side of the table, I'd probably do the same as well. But knowing what I know now, I'd be much more, instead of taking a 50% safety margin, nowadays I'd be saying I'd take 90% of what they're saying and put that in place. But when you start with little steps and move upwards.
Yeah. I understand that. Everyone wants to be cautious to make sure the end product isn't negatively affected.
Absolutely, yeah. Yeah.
Well, are there any other things about, the enzymes or fibers or phosphorus or calcium that we haven't touched on that you want to mention?
I don't think so. I mean, it's an interesting and fast evolving industry. I think what we're going to see is with time, I think, particularly, I think there's going to be a couple of interesting developments. Certainly in the fiber degrading enzyme side of things, there's a lot more work going on and a lot more understanding and a lot more information coming out with regards to fermentation and what kinds of fibers are fermented. And, some of the interesting things that we've discovered is that in many respects, what we're doing when we're using enzymes and what we're doing when we feed the xylo oligosaccharides and the combination we're calling a symbiotic, very, very small amounts of these very small xylo oligosaccharides are all that's needed for a bacteria to pick it up and say, woo, there's xylan out there. This is a molecule that's being produced as a result of xylans being broken down, and the bacteria recognize xylo oligosaccharides and they start producing absolutely bucket loads of their own enzymes to digest fiber. So it's a stimulating molecule. It's not digested by the bird. It's not absorbed by the bird. It's picked up incredibly. I mean, we're talking grams per ton is all that's needed to actually
That's
create
incredible.
this effect. Yeah, and that is what we're trying to do. Is we're not trying to provide the bacteria with all the feed that they need. We're trying to provide them with the signals to tell them it's out there, go and digest it. So that's one interesting area, because we do believe we don't probably today have found these signaling molecules, but there's quite a mishmash of different shapes and sizes. And I'm sure that somewhere in there is the real signaling molecules, which are much more effective than ones we got at the moment. So that's something we're working on. And then, with phytases, I think what we'll probably move to in the next 10 years is the recognition that actually the nutritional benefits that we're getting out of them in terms of the matrix we're applying, they're secondary to the other benefits we get with respect to, for example, what we just talked about, oxygenation of blood. But there's other factors we're finding on superdosing, which we're not really taking account of right now, not really understanding. So, it'd be interesting to see if that's right.
I mean, when you think about enzymes, you just think, oh, this is the function, this is the output. But then when you start thinking about these complex enzyme or other signaling molecule cocktails. That is really cool stuff. Just letting a bacteria know a substrate is available in enough quantity that it convinces itself and its friends that it's got to start making these other enzymes. I think that is like very cool.
It is, yeah. And actually, I think in many respects, we're fooling them because most bacteria will put out very small amounts of constitutive xylanases. So the enzyme that produces these little xylo oligosaccharides, and they're just throwing them out into the environment. And the idea is that if there's any xylan around, they'll produce some ZOS and they should diffuse back and tell the bacteria, yeah, this is worth committing. So what we're doing is basically preempting that and saying there is xylan out there, get going. And one of the responses as a result of doing this is if you start to feed these to very young birds, the bacteria in their ceca start to age and start to produce xylanases as much as 2 weeks earlier than a bird that is not exposed to those molecules. So they're they're much better trained to jump onto the xylan and produce the volatile fatty acids than untrained bacteria. And as a result, you don't get the sort of you know how birds in the sort of 15 to 22 day transition period when everything seems to go wrong, well, at least if you stabilize the back end of the gut to be ready to digest xylan, then you've got a much more stable microbiota and a more robust environment to keep pathogens at bay.
The stuff that we ask birds to do with the shortened growth timeline is just incredible. And with microbiologists, and the more I learn about the bacterial landscape, I'm glad I'm not a microbiologist because it's so complex, but I can appreciate working with them because you can only know so much about one field, and then having someone else's expertise to come together for collaboration is incredible.
No, that's right. Yeah, and that's actually that's one of the points about my job is I've never claimed to be a microbiologist or an expert in microbiology, but I work with some really, really good ones. And so I in many respects, I'm a jack of all trades. So, but I know enough in many areas to be dangerous and understand what is relevant in one field to the next field. And that's been the fun part of the job. And it really has been fun. I mean, if I go back to the guy who offered me the job, I wish I could go back and thank him because I'm glad I took the direction I did. Certainly, it's been a lot of fun. I've really enjoyed it. I still love the job I'm doing right now.
That's exciting. Well, this has been really, really fun talking to you and learning about these kind of up and coming areas as far as feed additives go. I'll end our conversation today asking you the 3 questions that we ask everybody. So my first question is, what is your favorite poultry-related book?
That's a rotten one to throw at me at this point in time because you're probably thinking it's going to be, I think I have a granddaughter now, so I would say Chicken Little. It's going to be the one, just a great story to talk to her about. And maybe use it as a means to introduce the next generation of poultry scientists to,
that's great.
Yeah.
What is your favorite or something you're reading right now that's non-poultry related?
Yeah, it's actually just been made into a film. I don't know if you've seen it. It's A Man Called Otto with Tom Hanks.
Yes.
Oh, it's brilliant.
Yes.
He's just such a cantankerous fella. And honestly, when I sat there, my wife read it and she handed it to me and she said, I want you to tell me what you think of this book. And I read it and I said back to her, I said, you think that's me, don't you? And it's funny, there's a lot of me in that individual. There's a lot of that individual in me, but I just thought that whole show was fantastic. I really did. It's just the difficulty that individual had in really expressing things correctly. I don't think I'm that bad myself, but I do see an awful lot of it in the way I interact. Yeah.
I had a colleague recommend that to me, and I found out there are 2 different versions. There was one, I can't remember if it was made in Sweden or the Netherlands.
Yeah.
But I'm pretty sure I found it on Amazon Prime or Netflix, and I watched that version first before the Tom Hanks ones. But
oh no,
they're slightly different. It's amazing. They're both based on the same story, so it's so interesting how 2 different filmmakers kind of took liberties, but it's a great story. I love it.
I think the thing that struck me as well when we first went in to watch it, I think it's like 2 hours and 20 minutes. It's a long movie.
Yeah. It's
But when
long. Yeah.
but when we came out, we realized, gosh, that's gone quickly. So yeah, it was really well done. I've always liked Tom Hanks. Yeah, yeah, great.
It's because you're on this like roller coaster of being really happy for him and then being really sad and then going
Yeah,
back
that's
to
right.
being happy and then going.
I know. Yeah,
Yeah.
it's quite an effective movie. It really was very good indeed.
Yeah. It was yeah, well done. So my final question for you today, and you've kind of been answering this as you go, but how you had advice for somebody entering the poultry industry, how can you be successful, or what sets people who are successful apart from those who are not?
I think it's being able to, it's important to relate to people as it is to the knowledge. And it's being able to understand and communicate complex ideas to all walks of life and recognize that you can really learn from everybody. There's nobody I've talked to. I mean, I go out and talk to nutritionists in Asia, in Europe, in North and South America, and you can be talking about the same topic, but you could learn so much from each of those individuals because they've got a totally different perspective on what you're talking about. And they bring information back to you, which enables you to be more effective in your own job. So, yeah, I would say it's down to communication. It's down to meeting people, and it's down to being not being afraid of going into disciplines which scare you, like microbiology. Is the point you made, but I was absolutely frightened silly with that. And now I met some good microbiologists, some of them now best friends, and I realized, that was a good move, a really good move. And actually, do you know, when I was at university, before I got the chicken project, there were two things I hated most were digestive physiology and statistics. What happened? You
made a PhD out of it.
I know exactly. And it just shows you that sometimes things you think you don't like because you didn't understand them. And it's only when you get to understand them that you realize, actually, this is pretty cool.
Yeah. Oh, I agree. I'm right there with you. Well, thank you so much for your time today. This was really a treat. I've learned a ton from you, and it was really exciting to be able to talk to you.
That's great. Well, that was really good fun as well for me. And thanks very much for setting that up for this.
Yeah.
It's been really good for me.
You are welcome. Thank you.
Okay. Talk to you later. Bye-bye.